Hello, Matrix. Let's start with an example. First is the ground truth sample, and second is the synthesized voice. Listen carefully.
Thy cold bed, and leave my shining lot. Cold bed, and leave my shining lot.
Welcome to WS Matrix. We're going to give an in-depth explanation of how voice cloning works by explaining the paper published in January 2023. Neural codec language models are zero-shot text-to-speech synthesizers by Microsoft researchers. Check out their paper in the link in the description. In the past decade, text-to-speech (TTS) systems have seen significant advancements, but still struggle with generalization, especially with zero-shot scenarios. The proposed solution is Vall-e, a language model-based TTS framework that utilizes large and diverse multi-speaker speech data, a departure from traditional methods that used a smaller amount of high-quality studio data. Vall-e generates acoustic tokens conditioned on the enrolled recording and the phoneme prompt, leading to personalized speech synthesis. Vall-e was trained on what's referred to as library light, which is a corpus of 60,000 hours of English speech from over 7,000 speakers. It's significantly larger than previous datasets. It outperforms the state-of-the-art zero-shot TTS systems in terms of speech naturalness and speaker similarity, and is even comparable to human recordings. Additionally, Vall-e can synthesize diverse outputs from the same text and maintain the acoustic environment and speaker emotion of the prompt. Here's another example. Listen carefully. First is the ground truth speaker emotion that expresses anger, and second sample is the synthesized voice.
Her face was against his breast. We have to reduce the number of plastic bags.
Text-to-speech synthesis, or TTS, is the task of generating human-like speech from text. It is a challenging problem due to the complexity of human speech, which is affected by a variety of factors, such as the speaker's identity, accent, and emotion. Traditional text-to-speech systems traditionally used a pipeline approach, which consists of three main stages. Text analysis. In this stage, the text is converted into a sequence of phonemes, which are the basic units of human speech. Feature extraction. In this stage, features are extracted from the phoneme sequence, such as MEL spectrograms, which represent the spectrum of human speech. Signal synthesis. In this stage, the features are used to generate a waveform, which is the actual audio signal that is heard by the listener. The pipeline approach has several limitations. First, it is difficult to train the different stages of the pipeline to work well together. Second, it is difficult to modify the output of the system, such as the speaker's identity or emotion. In the past decade, significant advancements have been made in speech synthesis through the use of neural networks and end-to-end modeling. Current text-to-speech (TTS) systems leverage a pipeline with an acoustic model and a vocoder using MEL spectrograms as the intermediate representations. However, these systems often require high-quality data from recording studios and struggle with generalization, particularly when dealing with unseen speakers in a zero-shot scenario. Existing solutions for zero-shot TTS involve methods like speaker adaptation and speaker encoding, but these often require additional fine-tuning, complex pre-designed features, or heavy structure engineering. An alternative approach is to train a model with large and diverse data, as has been successfully done in the field of text synthesis. The researchers introduced Vall-e, the first language model-based TTS framework that leverages large, diverse, and multi-speaker speech data. Vall-e generates acoustic tokens conditioned on the acoustic tokens of a 3-second enrolled recording and the phoneme prompt, which constrain the speaker and content information respectively. These tokens are then used to synthesize the final waveform. Vall-e uses advanced prompting-based large model techniques, similar to those used in GPT models. Vall-e is trained with library light, a corpus consisting of 60K hours of English speech from over 7,000 unique speakers. The data is more noisy and contains more inaccuracies than previous TTS training datasets, but it also provides a diverse range of speakers and prosodies. The researchers believe that this approach is robust to noise and can generalize well with large data. Vall-e significantly outperforms the state-of-the-art zero-shot TTS system in terms of speech naturalness and speaker similarity. It also produces diverse outputs with the same text and target speaker, can maintain the acoustic environment and emotion of the acoustic prompt, and does not require additional structure engineering, pre-designed acoustic features, and fine-tuning, as in previous work. Researchers believe that the development of Vall-e represents a significant contribution to the field of TTS, and that the model's in-context learning capabilities, ability to provide diverse outputs, and superior performance in the zero-shot scenario demonstrate its potential. Text-to-speech, TTS, systems are what allow computers to convert written text into spoken words. They can be broadly divided into two types: cascaded and end-to-end. Cascaded systems use a two-step process where an acoustic model and a device called a vocoder are used to convert the text to speech. End-to-end models, on the other hand, combine these steps into one. Imagine you want a TTS system to mimic your voice or the voice of someone else based on just a few recordings. This is where a concept called zero-shot TTS comes in. In this context, zero-shot means the system hasn't been specifically trained on that voice before, but it's still able to generate it. This is a growing area of interest in the field of TTS. Early attempts to achieve this use techniques like speaker adaptation and speaker encoding. Think of it as a way to tweak the system to better mimic the target voice. Some research has focused on making these tweaks more efficient, so you need less data from the target speaker. Another approach is to use speaker encoding, which is a system that contains a speaker encoder and a TTS component. The speaker encoder can be pre-trained to verify a speaker's identity. These systems have shown good results with just 3 seconds of a speaker's recordings. However, there is still room for improvement. More advanced, but complex, speaker encoders are being designed, and even models based on diffusion, a way of generating new samples from existing ones, have been extended to zero-shot TTS and have shown good results. Vall-e, the system we're discussing here, uses a different approach. Instead of tweaking and tuning, it uses a large amount of data and learns in context, much like the GPT-3 language model. It's the first of its kind to use this method. Second part is spoken generative pre-trained models. Spoken generative pre-trained models are a type of artificial intelligence that is trained on a large amount of speech data. They can generate new speech based on what they've learned. One hot topic in this area is synthesizing speech without needing text. Imagine being able to create spoken words without having to write anything down first. Several models have been proposed to achieve this, some of which use something called Hubert codes. Another approach is to pre-train neural TTS systems. This involves training them on a large amount of data before they are fine-tuned for a specific task. This method has shown improved performance in speech editing and synthesis. However, previous TTS pre-training work uses less than 1,000 hours of data. Vall-e, in contrast, is pre-trained with 60,000 hours of data. It's also the first to use audio codec codes as intermediate representations, a kind of bridge between the text and the speech, allowing it to learn in context for zero-shot TTS. Audio is typically stored as a sequence of 16-bit integer values, which can create over 65,000 probabilities per time step for synthesizing raw audio. When considering audio sample rates exceeding 10,000, this leads to an extremely long sequence length, making raw audio synthesis complex. To address this, a method called speech quantization is used to simplify integer values and sequence length. One approach is the mu-law transformation, which reduces each time step to 256 values, thereby enabling the reconstruction of high-quality raw audio. Although this technique is widely adopted in speech generation models like WaveNet, it doesn't reduce the sequence length, resulting in slower processing. A more recent approach involves vector quantization, used in self-supervised speech models for feature extraction. Models such as VQWave2Vec and Hubert employ this method, allowing faster audio processing than WaveNet. However, these models often lose speaker-specific information and the audio reconstruction quality can be low. An alternative model called AudioLM addresses these issues by training speech-to-speech language models on tokens, small chunks of data, from a self-supervised model and a neural codec model, leading to high-quality speech-to-speech generation. Neural codec models, which are used to compress audio for network transmission, are capable of converting waveforms into discrete acoustic codes and reconstructing high-quality waveforms, even when the speaker was not seen during training. These models, compared to traditional audio codec methods, perform significantly better at low bit rates while preserving sufficient information about the speaker and recording conditions. The model used in the described method is called Codec, a pre-trained neural audio codec model. This model drastically reduces the sampling rate and outputs high-quality audio. It uses a method called residual vector quantization to generate discrete representations of the audio. Depending on the chosen bitrate, the number of quantizers, units that turn continuous signals into digital ones, and the quality of the reconstruction will vary. For instance, a higher bitrate leads to more quantizers and better quality. The convolutional decoder in Codec then uses these discrete codes to generate high-quality waveforms. The research presents a novel method for generating text-to-speech audio samples using a system called Vall-e. The goal of Vall-e is to generate high-quality speech for unseen speakers, a challenging task referred to as zero-shot TTS. It requires model to synthesize high-quality speech for unseen speakers. Vall-e treats this as a conditional codec language modeling problem. It begins with a dataset composed of phoneme transcriptions and their corresponding audio samples. Pre-trained neural codec model is used to convert each audio sample into a set of discrete acoustic codes. These codes can then be recombined by a decoder to reconstruct original audio. Vall-e treats this as a conditional language modeling task in order to generate a specific acoustic code matrix based on a given phoneme sequence and an acoustic prompt matrix. The acoustic prompt matrix is created using the same neural codec, but with a different input, an enrolled recording from a specific speaker. The expectation is that the language model will learn to extract both content and speaker information from the phoneme sequence and the acoustic prompt, respectively. During inference, a phoneme sequence and a 3-second enrolled recording of the unseen speaker are provided. The acoustic code matrix that corresponds to the content and the voice of the speaker is estimated by the trained language model, and then the neural codec decoder synthesizes the high-quality speech. The training of Vall-e involves a unique approach that leverages the hierarchical structure of the tokens generated by the neural speech codec model. Some tokens capture the broader acoustic properties, like the speaker's identity, while others capture finer acoustic details. This hierarchy is used to design two types of language models, autoregressive, AR, and non-autoregressive, NAR. The AR model is trained using tokens from first quantizer. It's conditioned on the phoneme sequence and acoustic prompt. It doesn't differentiate between them or insert a specific token during training. During inference, only the phoneme sequence is predicted, while the acoustic prompt is given. On the other hand, the NAR model is trained using tokens from the second to the last quantizers. Since the tokens can't access each other in a non-autoregressive manner, the acoustic prompt matrix is used to constrain the speaker's identity. It is conditioned on the phoneme sequence, acoustic prompt, and predicted acoustic tokens that belong to previous codebooks. Combining the AR and NAR models provides a good balance between speech quality and inference speed. AR allows for flexibility in predicting the length of the acoustic sequence, which is important given the variability in speaking speed across different speakers. But NAR model can reduce the time complexity of the second stage of the process. The autoregressive language model is used to generate tokens from the first quantizer. It consists of a phoneme embedding, an acoustic embedding, a transformer decoder, and a prediction layer. During training, the model input is the concatenation of the phoneme sequence and the tokens from the first quantizer, with special tokens added after each of them. The model is optimized to maximize the probability of the next token in the first codebook. During inference, given an enrolled recording, the phoneme sequence of the enrolled recording is concatenated with the phoneme sequence for synthesis. At the same time, the acoustic token sequence of the enrolled recording is used as the prefix in AR decoding. The non-autoregressive language model is used to generate tokens from the second to the last quantizers. It consists of a phoneme embedding, an acoustic prompt embedding, a transformer encoder, a transformer decoder, and a prediction layer. During training, the model input includes the phoneme sequence, the tokens from the first quantizer, and the acoustic prompt, while the target is the token from the current quantizer. The transformer encoder is used to process the phoneme sequence and tokens from the first quantizer, with the goal of summarizing the acoustic condition into a fixed-length vector. Then, the transformer decoder generates each token from the current quantizer based on the encoder output and the acoustic prompt. During inference, given the phoneme sequence for synthesis and the acoustic prompt from the enrolled recording, the model generates tokens from the second to the last quantizers. This is achieved by conditioning the model on the phoneme sequence, the predicted tokens from the first quantizer, and the acoustic prompt. The autoregressive language model is used to generate tokens from the first quantizer. It consists of a phoneme embedding, an acoustic embedding, a transformer decoder, and a prediction layer. During training, the model input is the concatenation of the phoneme sequence and the tokens from the first quantizer, with special tokens added after each of them. The model is optimized to maximize the probability of the next token in the first codebook. During inference, given an enrolled recording, the phoneme sequence of the enrolled recording is concatenated with the phoneme sequence for synthesis. At the same time, the acoustic token sequence of the enrolled recording is used as the prefix in AR decoding. The non-autoregressive language model is used to generate tokens from the second to the last quantizers. It consists of a phoneme embedding, an acoustic prompt embedding, a transformer encoder, a transformer decoder, and a prediction layer. During training, the model input includes the phoneme sequence, the tokens from the first quantizer, and the acoustic prompt, while the target is the token from the current quantizer. The transformer encoder is used to process the phoneme sequence and tokens from the first quantizer, with the goal of summarizing the acoustic condition into a fixed-length vector. Then, the transformer decoder generates each token from the current quantizer based on the encoder output and the acoustic prompt. During inference, given the phoneme sequence for synthesis and the acoustic prompt from the enrolled recording, the model generates tokens from the second to the last quantizers. This is achieved by conditioning the model on the phoneme sequence, the predicted tokens from the first quantizer, and the acoustic prompt. Now let's talk about enrollment and how this ties in. Enrollment is the process of producing an acoustic prompt that can be used to condition the speech synthesis. This is done by taking a short voice recording and processing it with the neural speech codec model to obtain the tokens. The first several tokens are then selected as the acoustic prompt. This process ensures that the synthesized speech will have the same characteristics as the speaker in the enrollment recording. This approach allows Vall-e to adapt to a new speaker given only a few seconds of their speech. Additionally, it enables Vall-e to generate high-quality speech even with a small number of parameters. Next, we discuss the concept of in-context learning as it relates to text-to-speech (TTS) systems. In-context learning refers to the ability of a model to predict outcomes for unseen inputs without additional fine-tuning or parameter updates. In terms of TTS, it would mean a model could generate high-quality speech for unseen or new speakers without needing further adjustments. Unfortunately, existing TTS systems have not demonstrated strong in-context learning capabilities as they either require additional fine-tuning or the quality of their output decreases significantly for unseen speakers. To facilitate in-context learning in a zero-shot scenario, a situation where the model has not been specifically trained on any examples of the task it's trying to perform, the team designed special cues, referred to as prompts. The text to be spoken is converted into a phoneme sequence. A phoneme is the smallest unit of sound in speech, and an enrolled recording is encoded into an acoustic matrix. These form the phoneme prompt and the acoustic prompt. Two models, the autoregressive (R) and non-autoregressive (NAR) models, use these prompts. The AR model uses a sampling-based decoding method conditioned on the prompts, as the commonly used method, beam search, may cause problems. Sampling-based decoding can also increase the diversity of the output. The NAR model, on the other hand, uses a method called greedy decoding to choose the highest probability token. The final output waveform is generated by a neural codec decoder based on 8 code sequences. Two specific implementations of this approach, Vall-e and Vall-e Continual, are also introduced. Vall-e generates content for unseen speakers using a given text sentence, a segment of the enrolled speech, and its corresponding transcription. The transcription phoneme of the enrolled speech is added to the start of the phoneme sequence of the given sentence as the phoneme prompt. The acoustic prefix is used as the first layer acoustic token of the enrolled speech. With these prompts, Vall-e generates acoustic tokens for the given text, mimicking the voice of the speaker. Vall-e Continual is used in a slightly different setting. It uses the whole transcription and the first 3 seconds of the utterance as the phoneme and acoustic prompts. The model is then asked to generate continuations. The inference process is the same as with Vall-e, but in this case, the enrolled speech and the generated speech are semantically continuous. Vall-e was tested using the Library Light dataset, comprising of 60K hours of unlabeled speech from approximately 7,000 unique speakers, was used for training. A hybrid deep neural network hidden Markov ASR model was trained on 960 hours of data. Hidden Markov model was used to model the probability of phoneme sequences. The AR and NAR models, both with transformer architectures, were trained using 16 NVIDIA V100 GPU. Vall-e was compared with the prior state-of-the-art zero-shot model called your TTS, a speaker verification model, Wave LMTDNN, or waveform, language model time delay neural network, to estimate similarity between prompt and synthesized speech. Synthesis robustness is also evaluated to assess deletion, insertion, and replacement errors due to wrong attention alignments by calculating the WER word error rate. To determine speech naturalness and speaker similarity, comparative mean option score (CMOS) and similarity mean option score (SMOS) were calculated through crowdsourcing. 12 and 6 native speakers were invited as CMOS and SMOS contributors, respectively. Vall-e showed robustness and speaker similarity compared to the your TTS baseline. The word error rate could be reduced in the Vall-e Continual setting. Vall-e also outperformed other speech-to-speech generation models in terms of robustness. Here's an example. Pay close attention.
Nigh cold bed, and leave my shining lot. O bed, and leave my shining lot.
They moved thereafter cautiously about the hut, groping before and about them to find something to show that Warrenton had fulfilled his mission. Thereafter cautiously about the hut, groping before and about them to find something to show that Warrenton had fulfilled his mission.
The human evaluation showed that Vall-e's synthesized speech was similar to the given unseen speaker in testing and significantly outperformed the baseline in zero-shot scenarios. It also indicated that the proposed method could synthesize more natural realistic speech compared to baselines. An ablation study on the NAR model showed that the model without any prompts performed poorly on both automatic speech recognition and speaker similarity evaluations. Adding the phoneme prompt significantly reduced the word error rate, and using both phoneme prompt and acoustic token prompt improved speaker evaluation quality. For the VCTK evaluation, Vall-e outperformed the baseline in synthesizing speech with higher speaker similarity. Human evaluation on this dataset showed that Vall-e had better speaker similarity than the baseline and also performed significantly better in naturalness. It can also maintain same acoustic environment as well as mimic the speaker's emotions. I'm going to show you both examples. First is the acoustic environment maintenance. Acoustic environment maintenance ensures that the generated audio is consistent with the acoustic environment of the input. This is important because it helps to ensure that the generated audio is realistic and believable, as it helps to create a sense of continuity between the input text and the generated audio. Pay close attention.
Right. What'd you like about One Flew Over the Cuckoo's Nest? I think it's like, more convenient too. I think it's like, more convenient too. I think it's like, more convenient too. I think it's like, more convenient too.
We have Japanese fighting fish. We have to pay, obviously, a security fee just in case she would damage something, but we have to pay hazardous security fee just in case she would damage something, but we have to pay, obviously, a security fee just in case she would damage something, but we have to pay hazardous security fee just in case she would damage something, but
this is where that line has been. Everything is run by computer, but you got to know how to think before you can do a computer. Everything is run by computer, but you got to know how to think before you can do a computer.
Say, oh my God, I've got really bad PMS.
As friends saying, I've got more male friends.
As friends saying, I've got more male friends.
In the next example, I'll show you Pay Speaker's emotion maintenance, which is the ability to capture the speech emotion and synthesize similar emotions. Follow the mouse movement. First will be the ground truth sample, which is the actual sample of the speaker, and then compare it to Vall-e, which is the synthesized voice. Pay close attention.
Her face was against his breast. We have to reduce the number of plastic bags.
Check down and dig in. We have to reduce the number of plastic bags.
Do you know that you are shaking my confidence in you? We have to reduce the number of plastic bags.
That's what Carnegie did. We have to reduce the number of plastic bags. Matt, she said. We have to reduce the number of plastic bags.
Overall, the results indicate that Vall-e is a robust and effective model for text-to-speech tasks, high speaker similarity, naturalness of synthesized speech, reduced word error rate, and effective performance in zero-shot scenarios. In this research, a new text-to-speech TTS, system named Vall-e is introduced. Unlike previous TTS systems that have a strong one-to-one mapping between input text and output waveform, Vall-e employs a sampling-based method to generate discrete tokens, which introduces a degree of randomness, leading to diverse outputs for the same input text. This is illustrated in this figure, where two samples with the same input have different lengths, phrase durations, and accents. The diversity feature of Vall-e holds significant potential for various applications. For instance, speech recognition systems can benefit from diverse inputs, including different speakers and acoustic environments, a scenario that previously could not be achieved by existing TTS systems. With its diversity feature, Vall-e is a promising candidate for generating pseudo-data for speech recognition. Vall-e is also found to maintain acoustic environment consistency between the acoustic prompt and the generated output. If the acoustic prompt has reverberation, Vall-e can synthesize speech with the same feature, while baseline systems would output clean speech. This is attributed to Vall-e being trained on a large-scale dataset consisting of a variety of acoustic conditions. Interestingly, Vall-e can also preserve the speaker's emotion in the prompt, even without fine-tuning on an emotional TTS dataset. This capacity to retain the emotional context is highly valuable in the field of emotional TTS, a subtopic of speech synthesis. Despite these advancements, Vall-e does have limitations. In some instances, words may be unclear, missed, or duplicated during speech synthesis due to the phony new acoustic language parts autoregressive model. Additionally, even with 60K hours of training data, the system doesn't cover all voices, particularly accent speakers. The model also lacks sufficient diversity in speaking styles. Future improvements include leveraging non-autoregressive models or modifying the attention mechanism, scaling up the training data, and refining the model structure. Potential broader impacts of Vall-e include potential misuse, such as spoofing voice identification or impersonating a specific speaker. To mitigate these risks, the researchers propose building a detection model to discriminate whether an audio clip was synthesized by Vall-e, as well as applying responsible AI principles to future development. That wraps up this exciting development in the field of artificial intelligence and TTS systems. If you found this video informative, remember to leave a comment down below. What do you think about Vall-e and its potential impacts? Don't forget to give us a like if you enjoyed this content, and hit that subscribe button to stay updated on more fascinating AI topics. Thank you for tuning in.